All right, hello everybody. Today I've got something maybe interesting for you guys. I've been reading, as you know, I've been reading a bunch of old science fiction recently. I've been reading the Lensman series, and I've been reading Massacre of Mankind, which is the sequel to H.G. Wells, which is a sequel to H.G. Wells' War of the Worlds. And one of the things I'm noticing about old science fiction is that you can make, in the old days, you could make hard science fiction without as many restrictions because we knew less. Does that make sense? For example, I'm gonna just post this bit by bit, and hopefully I can walk you guys through it. In the Lensman series, the way that they do space travel, extremely high velocity space travel, is they put a bunch of rockets onto a ship, and then they also put a drive onto a ship that basically takes its rest mass to zero, right? Now, nowadays we know that from modern general relativity and kind of an understanding of that stuff, we believe, scientists think, that if you took the rest mass away from something, if you made its rest mass zero, then its velocity would be, basically hard-coded to the speed of light. That's how fast massless particles move in the universe, to the best of our understanding. And also, to the best of our understanding, there's nothing that moves faster, although people have hypothesized that there might be particles that have a negative mass, that they always move faster than the speed of light, and the more energy you give them, the slower they go, getting closer and closer to the speed of light. So nowadays, if you were to write hard science fiction, you would already know that there's this kind of universal speed limit of the speed of light, of c, approximately 3 times 10 to the 8 meters per second. But here's the thing. If you're writing science fiction the days before we understood that the speed of light was a universal speed limit, you could make the assumption that, hey, let's just take the rest mass away from a thing. We also don't know that taking the rest mass away from a thing locks its speed to the speed of light. And so we just say, well, what if we have a device that has zero mass but somehow creates thrust, right? Then how do we figure out how fast it goes? Well, we simply use a standard drag equation. So here we go. I'm going to put up on the screen right now an equation. I got this off of some random website. I think it might be something I got from a NASA website, but that doesn't necessarily mean anything because, who knows how good their webmasters are. But let's just assume it's about correct, because I did get it confirmed on a bunch of different places as I looked for this. But here we go. You see that this equation has several different parts to it. The first part is a letter D. The letter D indicates the drag force, right? So when we are creating the system of a rocket that has a thrust, and then it's only, and no mass, and its only limit to its speed is based on the amount of drag that it is feeling going through the interstellar medium, we're going to equalize this drag force with the thrust of the rocket that we're going to use. So we see here that force, D, or thrust, is going to be equal to CD, and I don't know why they didn't do a subscript here, but this should be C sub D, which is the drag coefficient. It's a number, it's unitless, and I looked it up, and depending on the viscosity of the stuff that it's going through and the speed and all that stuff, the lowest value for CD for a sphere is about 0.1. Here's the thing that's fun that I just looked up. For a teardrop, it actually can dip as low as, say, 0.01, almost a factor of 10, but a better average number, I'm going to put up a plot here from a paper that I found that models teardrop movement through viscous fluid, is, say, 0.025. And this is why teardrops go faster than spheres in the Lensman series. Now our next thing is called rho. Rho is the density that we're going through. Now I looked this up. In the interstellar medium, the primary stuff that you have there is molecular hydrogen, H2. Generally speaking, what we believe that we expect to find out there is about 10 to the 12 molecules. That's a 1 with 12 zeros after it, molecules per cubic meter of hydrogen, H2. Now that sounds like a lot, but it's actually not that much. The actual density of such an interstellar medium is really only about 3.32 times 10 to the minus 15, 0.00000000332 kilograms per meter cubed. It's a medium that's extremely easy to move through because there's almost nothing there. Then v squared, v with the 2 in the superscript, is velocity of the object squared. That's how fast our hypothetical rocket is going to go. And then a is the frontal area. Basically, if you took a cross section of the spaceship, that in the plane of the direction that it's going, then that would be the area we're talking about. For a sphere, this is really simple. It's pi r squared. So if we assume, say, a 100 meter diameter spherical ship, then we get something like between 7 and 8,000 meters squared for this area. So you'll notice that nowhere in this equation is there anything related to the speed of light. Is there anything related to relativity? Is there anything related to time dilation? Is there anything related to any of that? This is a purely classical equation. And it's even a purely classical equation with a fudge factor. That's what the drag coefficient is, because drag as an effect is so complicated that the way that scientists kind of describe it is we say, oh, what's the drag coefficient of this thing at this rough velocity in a medium with this viscosity, and we just kind of give it a number and say, okay, that's the force we observe, and so we're going to assume that for a similar Reynolds number that it's going to have the same drag coefficient, and so you can make a function there. But that's getting even more complicated than we get. But my point here is that for the purposes of hard science fiction in the 1940s, this is a perfectly reasonable equation to put together. You're doing hard science, or at least you think you are, because you're ignorant of a lot of the things that science has figured out in the past 70 years. But here's what we get. Here's the best part. I looked up the thrust of a couple of different rockets. If you look at a single space shuttle rocket, of which I think there were actually 3 on the space shuttle, but let's just pick one for like a lower bound. That gives us about 2 million newtons of thrust. If we look at something else like the one of the rockets on the Saturn V device, you get actually closer to like 10 million newtons. So getting those is kind of like as a rough range. And of course, hypothetically, in this world of the Lensman, they might have thrown a bunch of rockets onto the thing and given it 100 million newtons or something like that of thrust. But let's just stick to like between 2 and 10 million newtons for the time being. If you calculate this out, if you do a little algebra, you can calculate the velocity as a function of the thrust, the drag coefficient, the density of the interstellar medium, and the frontal area of the ship. You get an equation that looks like this. V is equal to the square root of 2 times d, where d is the thrust force, divided by the quantity, drag coefficient times rho times area, end quantity. So it turns out that if you type in these numbers that I just gave you for the density of the interstellar medium, for the drag coefficient, for the area of a 100 meter diameter ship, for the force of these rockets that I just described, between 2 to 10 million newtons, or 2 to 10 million newtons, you get velocities of about 1.24 times 10 to the 9 meters per second, all the way up to, say, 5.54 times 10 to the 9 meters per second. And guess what? Those are both over the speed of light. And so we see that one of the great advantages, ironically, of old science fiction is that you can come up with different ways to calculate the rules of how the world works, because our knowledge of how those rules worked was less complete back then. You could completely ignore relativity and just say, I'm just going to equalize these 2 drag forces and we'll get a velocity that way. And as you can see, you can get superluminal velocities with totally reasonable rocket thrusts and stuff like that. And that's how I think Doc Smith came up with his superluminal ships. Get rid of the inertial mass. He doesn't know that if you get rid of inertial mass, you lock something to the speed of light, and then you just calculate the velocity based off of drag forces. Isn't that brilliant? We've got we got similar effects going on in what do you call it? In The Massacre of Mankind, in H.G. Wells' War of the Worlds. We have, a misunderstanding of what was going on the surface of Mars that contributes to the idea of there being like a subterranean civilization there, and bodies of ice. We have ideas about what it was only recently, civilizationally speaking, that we understood that the clouds covering the surface of Venus are like sulfuric acid clouds and not just like water clouds. And so, when H.G. Wells was writing The War of the Worlds, and when other writers of that time were writing about, the other planets, they had different ideas about how the solar system, came to be and how it coalesced and all that stuff. And the fact that they were working from that information gives them more leeway to come up with more, outlandish ideas, as opposed to modern, hard science fiction where the speed of light is a maximum speed, yada yada yada. I just thought this was really fascinating, and I thought it was really fascinating how using completely reasonable numbers, that you could get a superluminal speed just from equalization of drag. It makes the whole situation of like spaceflight in the Lensman make sense, and I did want to look at this to see that it does make sense. And these numbers are not particularly faster than the speed of light. 1.24 times 10 to the 9 is less than 1.5 times c, but you can see how, with a reasonable number of rockets and maybe a smaller ship, and using a teardrop, right? If we use a teardrop, our drag coefficient goes from 0.1 down to perhaps 0.01. You can gain a significant amount of speed. We notice that we've got that square root in there, and so you actually don't quite gain as fast as you think you would. But this is one of those things about hard science fiction, is that you actually have to use, not necessarily calculations, but you have to use the best understood, the best understanding of a particular field of science at the time that you're writing, right? You have to use your understanding of, whether it be physics or microbiology or whatever. These are all things that go into a good science fiction story, is that from the perspective of the writer, at the time of the writing, the things that are going on make sense in at least some physical perspective. And that's one of the things that I kind of enjoy about it, is thinking about, considering the average size of a gas giant that we're aware of, what is the minimum amount of time you could take for an orbit and not be within the atmosphere? Good question. But calculating these things is part of, and again, it's not necessarily calculations. It could be something about chemistry. It could be for instance, in Massacre of Mankind, they talk about the chemical combination through some kind of catalysis of oxygen and nitrogen into nitrous oxide to sequester the Earth's air. That's something that is in that book. And that's perfectly reasonable, considering that it doesn't, break everything. There aren't any, to put it in a very specific way, there aren't any perpetual motion machines, and there isn't anything that a person writing around that time would not have understood as a thing that might at least conceivably exist in the real world, which is kind of what separates the harder types of science fiction from the more fantastic versions of science fiction. But I just thought this was a neat little calculation. I thought it was neat to think about how writing in a period where the understanding of science is less complete gives the writer more leeway to come up with different ways to do stuff. And that might be one of the reasons why, old, hard science fiction still has so much creativity to it, because just by using a classical drag equation, you can come up with superluminal velocity, without like fiddling around with like wormholes and that picture that everyone always the picture that everyone always shows in movies, where you take a piece of paper and you fold it and you take a pen and you poke it through, and the 2 points are far away, but then you bend them and then they're close together. We don't need this. We don't need the 2 dots on a page on a folded piece of paper. We can ignore general relativity and just use a classical drag equation. I don't know. I thought that was fun. Maybe you will too. But this is one of the things that makes hard science fiction written 30, 50, 60, 70, 100 years ago a little bit more out there, because we just didn't know about these things. And I kind of think that's fascinating. So that's what I got for you for today. I hope you enjoyed that. Have a good weekend, everybody, and thanks for watching. Thanks for listening. If you like what I'm doing in the channel and you want to see more, you know what to do, and I will see you next time. Have a good weekend.